Underwriting for the production of Autoline this week has been provided by
Autoline is brought to you in part by the commercial vehicle brands of Tenneco, pioneering global ideas for cleaner air and quieter, smoother, and safer transportation.
BorgWarner, developing advanced technology specifically aimed at reducing emissions, increasing fuel economy, and improving performance. Our award-winning innovations extend from turbocharging and cooling systems to friction materials and diesel cold start technology. Built on a century-long reputation of innovation and reliability, we have the track record that proves our technology can help meet the challenges of the commercial truck and off-highway industry.
Deloitte's Automotive Group is at the forefront, driving transformation and tackling complex challenges. Whether you are interested in globalizing operations, optimizing supply chains, mitigating enterprise risk, or driving innovation, Deloitte can help develop solutions that create long-lasting value. To learn more about Deloitte's Automotive Group, visit us online at deloitte.com/US/automotive.
From the Autoline studios, here is your host, John McElroy.
I want to thank you for joining us on Autoline this week. You know, the automotive industry has got to come out with more advanced power plants. That could be battery electrics, it could be plug-ins, it could be fuel cells, it could be flow batteries. You ever hear of that one? Probably not. I just learned about it recently myself. But I've got three experts to talk about these technologies. Charlie Freese is the Executive Director of Powertrain Engineering at General Motors. Levi Thompson is a Professor of Chemical Engineering at the University of Michigan. And Jeff Kessen is the Vice President of Corporate Strategy for the battery company A123. I want to thank you all for joining us on the Autoline set.
Thank you.
Thanks for having me.
Thank you.
Charlie, I'll start with you. You've got a tremendous amount of experience in developing piston engines. Now you're in charge at General Motors of developing fuel cells. I've been hearing about fuel cells for so long now I can't remember how long it's been, but in your opinion, what's it going to take for fuel cells to replace piston engines?
Well, we've been on a dramatic pathway of cost reduction on fuel cells. We really started out in the 60s. GM started with the fuel cell program way back then. And there were a lot of technical challenges. It wasn't something that we could just do as a space program type thing where fuel cells were finding their route. We had to go in and advance it in terms of something you could package on a car. That was really one of the key challenges. And then make it so it can work over the dynamic load range of a vehicle. So as we pushed through those barriers, got it so it could cold start and do all those things, the power density started to improve, and we got to the point where it wasn't really that it was technically impossible to do it any longer. It was just the economics of it. So we started pushing through the economics and driving the cost out, which we've driven that down by orders of magnitude now. So what the fuel cell that is available today is already at a point where you can afford to put it in a car. The question is the value proposition right for the customer today? And that's the part we're working on right now. We're driving cost out. We're trying to make it so that there is a value proposition for the customer and it can drive the compelling reason for buy.
Jeff, same question to you, but from a battery standpoint, what's it going to take for pure battery electric cars to be able to replace the internal combustion engine, or can it?
Well, I think we've already come a long way. I agree with Charlie that the economics really at the end of the day are an important factor in how fast the adoption of the technology can happen. And because our industry is starting to reach significant scale, we're finding that the manufacturing cost of batteries has dropped fairly dramatically in the last few years, and it will continue to drop. And so if we would look back at some of the prognostications about battery price that were made perhaps 3 or 4 years ago, it looks like in 2020 we'll probably beat what the analysts were saying on average. And that's important to getting to a market where the consumer is interested in on an unsubsidized basis. We think that's an important turning point.
Good. We'll want to get into more details on all this, but I'm dying to ask Professor Levi Thompson about this flow battery, or I've heard it referred to as a flow cell. Mm-hmm. And please explain, don't get too technical on us now, make us be able to understand it, but Levi, what is that?
So a flow battery is in some ways a hybrid between a conventional battery and a fuel cell. You have a fuel, liquid fuel that is in one tank and some oxidizer in another tank. You flow them over a device that looks a lot like a fuel cell to power the vehicle or power whatever the application is. Then you reverse that flow and you can store charge. And so you could imagine that there's a lot of flexibility with regard to the materials that can be used, which offers some economic advantages, as well as, depending on where you live, you might opt to use one chemistry versus another. So it's a really, the best way to describe it is sort of a hybrid or a compromise between what you see in a battery, a conventional battery, and a fuel cell.
Even though most people have not heard of a flow battery, this is not a new idea, is it?
No. It's actually, the roots come from basically a rechargeable or regenerative fuel cell. And over the years, people have developed the technology to now be competitive for grid applications in particular. I'm not sure about automotive applications, but certainly for grid where...
Now explain that. What do you mean grid applications?
So grid applications, the cost has to be substantially managed, and there are issues of power density that you may not have with a vehicle. And so one of the nice things about the fuel cell, and it's a little bit like a flow battery, it's a little bit like a fuel cell, is that if I want to get higher power, I just flow the electrolytes more quickly. If I need higher energy density, I just put more stuff in those tanks. And so you have a lot more flexibility, and in design, designers want flexibility, in particular for grid applications, grid storage, and even, one of the interesting opportunities that this presents is the introduction of renewables, where there's a lot more variability. Sunlight is not there all day, and so wind is very variable, and so flow batteries look to be very attractive for those applications.
And my understanding is it doesn't run on anything like hydrogen. It runs on what they call an ionic fluid that somebody described to me as being like liquid salt with an electrical charge in it. Is that right?
That's right. Usually they have some organic and a little bit of metal in them, and the charge is stored on the metal and the organic. But you described it very well. Very simple, but very elegant.
Charlie, let's go back to fuel cells. Well, first of all, has General Motors even looked into flow batteries? Does that make sense for automotive or not?
Well, the challenge on a vehicle really is you've got to be able to refuel quickly. You've got to be able to package it on board the vehicle, and space is really a premium. You have two things that you really watch when you're talking about putting energy on board the vehicle. One is the volumetric efficiency of packaging the energy on board. The other is the mass. And both of those we watch very closely. Right now, from what we've seen, a flow battery at this point is probably going to be a little bit space intensive. So our direction has been that we're pushing toward either battery electric vehicles or fuel cell vehicles, depending upon what type of an application. There isn't really one silver bullet that solves all the needs of advanced propulsion. Different types of customers with different types of vehicle needs will be better suited with different types of technologies. And so we're trying to target the technology where it provides the best value for the customer.
Let's talk a little bit about fuel cells. I've heard that if you go back, not all that much in the past, that it cost an automaker about $1 million to be able to build a fuel cell system. That maybe that's down to about $50,000 right now. I know that's a big order of magnitude. Is that sort of directionally correct or not?
Well, the first prototypes were expensive, and that was because they were hand-built. Some of the Project Driveway fleet that you probably recall from about 2007 timeframe, some of those vehicles, the parts moved around the world a couple times before they actually landed where we were going to produce them, because we were doing development work and testing every single part. It was an experimental fleet at the time, and that runs the cost up. And even a conventional vehicle, if it's an experimental one-off or a very small fleet, it's expensive. But now we've driven the cost out dramatically. That Project Driveway fleet had over 80 grams of platinum to make the fuel cell work. Now kind of our workhorse in the laboratory runs under 30 grams of platinum, and the ones we're actually developing on the frontier of where we want to go and where we expect to have a viable system that can be competitive is under 10 grams of platinum. So we're moving dramatically down that pathway.
And I think anyone can understand the more platinum you can take out of any system, the more cost you're going to take out.
Absolutely. And if you start to think about the platinum, I mean, that is one of the key drivers, but now it's actually moving way down on our Pareto chart. The platinum is still a cost we keep an eye on, but we're down to the point where if you think of some diesel engines with after treatment, they have more precious metal than we're talking about putting in with a platinum system in the fuel cell.
Jeff, and let's talk cost with batteries, because my understanding, again, is that just a few years ago, it was about $320 per kilowatt hour. I'm told it's more like $270 right now, and that in just a few years' time, we'll be down to $240. Do those numbers sound right to you? And where do you think it might end up? You said 2020 might be the sweet spot in terms of cost.
I think those numbers are in the right range. There's a lot of variation in the data that you might find depending on whether you're quoting the price of the single cell or whether you're quoting a fully integrated system. So that creates quite a bit of noise in the market for what the price of the batteries actually are. And for a given program, there's also vehicle volume sensitivity that's a significant driver. But I would say when a battery manufacturer is running an EV plant at close to capacity, then the ranges that you highlighted are correct today for the cell level. Pack level would be somewhat higher. But in 2020, I think we could see another 25% perhaps come out by then.
What do you think it would take to really, flick the switch, so to speak, that people would say, I've had it with my internal combustion engine, I want to go with an electric? Or do they even think that? What do you think the cost proposition or the value proposition will be when consumers say, yeah, I really want an electric car? And when I say that, I mean, clearly we're selling electrics, or the industry is right now. I'm talking on a mass market basis.
So I think to answer that question first, we should talk about what does success look like? What's the penetration rate that would really be a significant achievement in the market? And I think many people that I talk to see 10% penetration to be really an outstanding result for the environmental concerns and also for the battery industry. In order to reach 10%, we're going to have a significant improvement in cost beyond what we see to 2020. And at the moment, frankly, it's quite hard to forecast where that might come from, because the original idea is that major battery breakthroughs were going to happen at the rate that silicon improves and the electronics industry has not come to bear. And I think the reason for that is there are so many different dimensions of battery performance that if you really focus on increasing the performance in one area, often the so-called breakthroughs have some compromises in the other areas. And so in order for a vehicle manufacturer to really consider putting a significantly new technology on the car, it can't regress in any of the areas that we have today. And as a result, I think we have more of an evolutionary process going on in battery technology as opposed to a breakthrough happening every second or third year.
I want to throw this out to all of you, and anybody jump in. Are we doing the right thing? I mean, you're focusing, Charlie, on reducing the cost of fuel cells. Levi, you're talking about the potential for flow batteries. Mm-hmm. Jeff, you're talking about, again, taking cost out of the battery cell. But I'm wondering, on a total life cycle basis, from cradle to grave, are these alternative power plants a smart way to go? There's a lot of mining. We're talking about platinum. There's manufacturing. My understanding is making batteries is energy intensive. And the recycling end, do we really just want to throw all this stuff in the landfill, or is there something else out of it? So who wants to take a stab? Are we doing the right thing from a total life cycle energy usage?
In my opinion, the regulations, or let's say the government incentives and pressure to improve fuel efficiency generally have the strongest potential to achieve some major improvements in terms of energy security and in environmental benefits. And to that end, the incremental steps in hybrids and in simpler systems, which have lower on cost, have fewer customer adoption barriers, and have a better overall economic value proposition, are happening. That's not where a lot of the discussion happens. There's a big focus on zero-emission vehicles, and there should be, because that's ultimately where I think we need to get to. But there's a long path to zero-emission vehicles on a broad scale. And in between, there are a lot of successes that our industries are achieving, but they're not quite so flashy. They're not big breakthrough numbers. And as a result, we maybe don't cover them as well. But to come back to your question, yes, I think the industry is driving in the right direction.
So if I were to make a comment, one of the things about life cycle analysis is that once you do it, you have some direction for improvement. You know, if you find that there's some challenges in a particular area, you can then start doing work. And so for me, the value of doing the analysis is kind of identifying what the next generation might look like. And so I don't think any of these are, certainly fuel cells have a lot of advantages over a sealed battery, and I think a flow battery is somewhere in between. But the next generation will be informed by whatever we've learned from both fuel cells and batteries, and as a consequence, I think it'll be better in many ways from a life cycle analysis perspective.
Everyone always likes to talk about fuel cells versus batteries, and I don't see it as an either or. Every fuel cell that we work on is a hybrid vehicle of some sort, because we're using the battery as a way to store the regenerative braking energy that comes out of stopping the vehicle, and that's the most efficient way to package it, because that means less energy we need to consume on board the vehicle to move it, and that means less hydrogen storage requirements and a smaller fuel cell, and everything else can be optimized. So when we go down this path, really the electrification of the automobile is inevitable. We are moving down that pathway, and so this is all part of that journey, taking the cost out, making it more affordable, and trying to get to the scale economies that can make it more affordable to more buyers.
Mm-hmm. But what about the energy that's needed to manufacture the hydrogen in the first place? And my understanding is most of it's made out of natural gas right now. So even though there's zero tailpipe emissions, that's why I'm asking about this total life cycle energy use. Is it really the right way for us to be going?
Well, that's today, right? And we're at when the first automobiles were out with internal combustion engines, you bought the fuel at pharmacies, right? I mean, it was cleaning fluids and things like that. So we're at a point now where maybe the most convenient way to get the hydrogen is by reforming natural gas, and that's where a lot of the distribution is connected, is through reformed natural gas pipelines and things like that. So all of those types of things are there today. What we're trying to do, though, is we're trying to move the next step, and really to wring all the advantages out of hydrogen, you need to think of the broader economy. You need to think outside of just automotive. You need to think outside of just where the fuel ultimately comes from. Certainly renewables are one key part of this. And when you start to expand the control volume and look at these other areas, that's where the real incentives are, because renewables today, think of wind. The wind doesn't blow when the maximum demand is on the grid. And so what you end up doing is curtailing that wind. You pay people not to make energy with their wind turbines at the points where the demand and the supply don't match. That's very wasteful. And so what we need is a way to buffer that. And one way to buffer that over the types of periods that the wind can go through, multiple days, maybe even weeks, where there's kind of an oscillation in the wind supply, you can do that best with hydrogen. It's a very dense way of storing the energy for longer periods of time. And once you've done that, now you've just changed the whole dynamic of it. You can use that energy either for putting it back on the grid, but that's actually not the best place to use the energy. It's to put it into vehicles, because we can make the biggest benefit by doing that.
But with the renewables, are you talking about electrolysis, i.e. separating hydrogen and oxygen from water? And what I'm really getting at is, has anyone looked at how much water that's going to take? You know, with so much talk being in the country, especially out in California, of a drought right now, where's all this water going to come from?
Well, we borrow the water.
What's that mean?
No, we borrow it. We give it back at the tailpipe, right? It's a temporary use of the water, and it's going right back out the tailpipe when we're done. It's not like we're consuming it and using it forever. And you don't have to start with the freshwater supply that everybody's trying to drink. You can use salt water. You can use other things. So there's a lot of ways to manage that. But one of the interesting things when you talk about water demand is in California, in Orange County, right now they're using wastewater treatment plants as a way to produce the hydrogen. So now you've just taken a way of cleaning the water, and you've used that to produce the hydrogen that's actually going into the cars. So you need to kind of expand the control volume, think about the overall economy and all these other sectors of it, and that's where really the big benefits come out. So right now, natural gas is a big source of it, but longer term, all of these other avenues can open up. Hydrogen's really just an energy carrier.
Gotcha. Jeff, coming back to this whole discussion about life cycle analysis, my understanding is that manufacturing batteries is energy intensive. They've got to be baked in ovens for weeks on end and the like. So again, same question, from a life cycle analysis, is this the right way to go?
So first let me offer a correction. It's not baking an oven for weeks. There are some parts of the process that are long in terms of aging of batteries, but that's not really where the energy consumption is in battery production. It tends to be in the process of charging the battery the first time and discharging it. When we're in the process of converting all the chemicals in a battery into a functioning battery, some energy is certainly consumed. But I think if you look on the total basis of what a battery electrified vehicle or what a hybrid or even what a low voltage hybrid can offer in terms of the life of the vehicle, the amount of energy consumed in production of the battery is actually close to negligible. It's not, it's a one-time introduction of the energy to the battery. It's not as if that's an ongoing demand. So, I think that there is an efficiency in the industry for sure.
The only reason I mentioned the baking is I was down at Nissan's battery plant in Tennessee where they make batteries for the Nissan Leaf, and they were baking those things for weeks on end. I say baking. Maybe that's not the right word to say, but it was
depends on what
temperature
temperature we're talking about.
Right.
Every battery chemistry and every battery manufacturing company has a different aging formulation and a different process. And so, at least speaking for A123, ours is not a high temperature process wherein much energy is consumed.
And how about at the opposite end, recycling? Because that can take energy too. And especially when you come to lithium-ion batteries, is there really much recycling taking place, and how energy intensive might that be?
Today there's not a lot of recycling going on because there's not a lot of batteries to be recycled yet. I mean, there have been a reasonable amount that are now installed in vehicles, but we expect those batteries to have 8, 10, 12-year lifetimes, perhaps even more if they go into a secondary purpose before recycling. And so the recycling industry, I would say, is still small compared to the production. What's encouraging for me is that if we look at the cost of recycling manufacturing scrap, and if we look at some of the other small sources of batteries that cause the recycling industry to grow up a little bit, we're finding now that it's possible to recycle a battery, and the recycler is getting enough value out of the recycled content that they want the batteries. It wasn't that long ago that we were paying significant amounts of money to recyclers to take what we had to have recycled. And so that gives me an encouragement that there is an economic value proposition to recycling. And today, not even all the potential is tapped, because today what's largely being recovered is the aluminum and the copper in a battery, not yet the expensive active materials. And so there's even more potential. And I think that as the supply of batteries needing to be recycled increases, that industry will certainly be ready for it.
Very interesting. Levi, I've introduced you as a professor of chemical engineering, but you're an entrepreneur. You started a battery company, and you're heavily involved in researching on fuel cells and on flow batteries. As you stand back and look at this whole discussion, where do you think automakers should place their bets?
That's a good question. The consumer ultimately will decide what product is introduced or moves forward. As a consumer, I have significant interest in battery-powered vehicles, partly because I see the efficiencies that you can get, but the cost is high. Fuel cells may be next. One thing that's interesting is that as you look at battery and fuel cell-powered vehicles, these are all electrification strategies, and I think ultimately, if we were to come back 20, 30 years from now, we'll see much higher degrees of electrification. So the work that we're doing now, I think, will be very valuable. From a research perspective, there are, as both have indicated, there are just these tremendous challenges that will require some out-of-the-box thinking, and I think that's where flow batteries come in. You know, it's a very different kind of system when you consider some of the advantages, disadvantages, the chemistry itself, and I'm not sure it's going to make it as an automotive, you know, power plant, but certainly for grid storage, there are some good options there, and we like them.
There is a startup company called Quant in Switzerland that it has stuffed a flow battery into a car, so it'll be interesting to see if they can really develop that. What about infrastructure, though? I mean, hydrogen infrastructure, smart grid, maybe ionic fluid. Charlie, how many new infrastructures can the country afford?
Well, I guess the way we need to think about this is some of these infrastructure investments are very similar when we talk about batteries or we talk about fuel cells with the hydrogen refueling infrastructure. It actually turns out to be about the same cost for a mature infrastructure if you put it in from beginning to end. The difference is that when you talk about battery charging, you're doing it at point of use. So you might do it in your home or at your place of business, and you have multiple recharging locations. Those might be less expensive, but a hydrogen infrastructure you can do where you can refuel 1,000 cars or more from a single station, much like we do with petroleum-fueled vehicles. So there is a difference in terms of the scale where it makes sense, and that really becomes the challenge going forward. Once the cost is out there at an affordable price and there's a value proposition for the buyer, you have to make sure that you concentrate that investment on infrastructure so it can support itself with the vehicles that are in that area. If you try to stretch too far too fast, you'll starve the station for cars, and then it becomes much more difficult to get to a valuable proposition for the station owner.
It's going to be fascinating to see how this all develops. It's amazing to me to see the automotive industry investing in so many different types of powertrains. But with that, we're going to have to wrap up this discussion. I want to thank all three of you for having come in today. Jeff Kessen, Vice President of Corporate Strategy at A123, Professor Levi Thompson at Chemical Engineering with the University of Michigan, Charlie Freese, the Executive Director of GM Powertrain Engineering. Great having you all here talking about these topics.
Thank you.
Thank you. Thank you.
And I want to thank all of you for having tuned in.
Underwriting for the production of Autoline this week has been provided by
Autoline is brought to you in part by the commercial vehicle brands of Tenneco, pioneering global ideas for cleaner air and quieter, smoother, and safer transportation.
Warner, developing advanced technologies specifically aimed at reducing emissions, increasing fuel economy, and improving performance. Our award-winning innovations extend from turbocharging and cooling systems to friction materials and diesel cold start technology. Built on a century-long reputation of innovation and reliability, we have the track record that proves our technology can help meet the challenges of the commercial truck and off-highway industry.
Deloitte's Automotive Group is at the forefront, driving transformation and tackling complex challenges. Whether you are interested in globalizing operations, optimizing supply chains, mitigating enterprise risk, or driving innovation, Deloitte can help develop solutions that create long-lasting value. To learn more about Deloitte's Automotive Group, visit us online at deloitte.com/US/automotive.